Okay, welcome to this section on climate change or transport and climate change. I know there are many more papers on climate change that are coming or presented here. So you certainly do not claim that this is the most important one, but it's a section that really deals with transportation and driving. Just a few words. Relative importance for climate emissions. I think cars are important to this kind of a world level. Many estimates, cars, trucks, shipping, aviation. Now these two are growing. Just to situate the story. There are actually three papers that will be presented. One paper on cars, mainly electric cars, so really already going to another type of technology. This paper will be ready soon, and if Maria is in the room, just ask her when it's available. Okay. Then there will be a paper by Kenneth Rødseth, okay, doing about shipping, because shipping is very often forgotten, but it's also an important element. And I will myself present something on aviation. The focus will be different. Here it will again be electric ferries, electric cars. Here we don't have electric planes, so we'll just move to just reducing emissions. Now, I know that most of these things have to do with the EU. EU is some kind of leader in terms of action on climate. US, China may follow. The important thing is that this can maybe serve as a good or as a bad example. And it also, because in the end, I believe that technology will be technology development. How we sustain technology development will be a major factor. Now I give the floor to Robin.
And this paper is joined with André de Palma, who's in the audience, and then Yannik, Riou, who's connected by Zoom, and it's a work in progress. The intent was to evaluate electric cars in terms of the private cost of ownership as well as the social cost. And so far, we've just looked at the cost of greenhouse gas emissions. And most of the analysis relies on Yannik Riou. He's currently at Beta, but for much of his career, he worked in the automobile industry. He has an engineering background, and he collected the data and did most of the calculations. So he's really the lead author of this study. But I don't think that electric vehicles require motivation, so I'm going to jump in now already to some of the statistics. There are some 500 models of electric vehicles in use today, compared to some 3,000 internal combustion engine vehicles. So there's still fewer electric vehicles than internal combustion, and that has implications for substitution. If someone wants to get an electric vehicle, which is as close as possible to the existing internal combustion engine vehicle, then they may not be able to do that, right? They're going to have something which may be more upscale or downscale. So there are trade-offs. As far as the power is concerned, of course, the internal combustion engine vehicle has only either a petrol or diesel, and it has a battery, but that's not for propulsion. Then we have hybrid electric vehicles with a very small battery, and they're recharged with the engine. There's no plug-in. The plug-in hybrid electric vehicle can be powered either by the ICE, internal combustion engine, or an external charger. And there's three types, level 1, 2, 3, which differ in the cost of obtaining them, as well as the rate at which the electricity is delivered. And then we have what you might consider to be the true electric vehicle, the battery electric vehicle. It has no internal combustion engine, so it has to be recharged externally. Now, we know there are various supportive measures for EVs, subsidies for buying the vehicle and the charging equipment, and then various recurring benefits, which would include paying no tolls and having reserved parking spaces. This is an incomplete list. And there are also contrary restrictive measures for internal combustion engine vehicles, minimum fuel efficiency standards, which began nearly 50 years ago, bans from zero emission zones. There was a talk yesterday about that. Bans on the sales, and they're coming in the year 2035 in Europe. And then, and I don't know about whether this has actually been proposed yet, bans on operating ICEVs. That will probably be some time off, but it could well come. So what are the advantages of electric vehicles? Well, there are private benefits, lower energy costs, simpler engines, no emissions control equipment, and regenerative braking, which means that when the vehicle is being stopped, the battery can be recharged. It means less wear and tear on the brakes and so on. And those are the main reasons for lower maintenance costs. Now, the maintenance costs are going to vary. Things are going to change pretty quickly over time. So the data we use will probably become obsolete fairly quickly. Now, what about the social advantages? Well, fewer greenhouse gas emissions, but not zero unless you have a green energy source for the production of electricity. No local pollution. But there's still barriers to the adoption of electric vehicles, although they're diminishing over time. And here's a list that includes the driving range, and that's temperature sensitive, public charging infrastructure, and the subsidies for spending that, and then the amount of time required to charge, and that'll be much less for the level 2 than level 1. But level 3 apparently can damage the battery, so its lifetime would be reduced. So what do we do in this paper? Well, we're going to make a comparison of electric vehicles and internal combustion engine vehicles and try to match them up as closely as possible. That's not always the case. The acquisition costs, the operating costs, and the greenhouse gas emissions. And the focus is more on the difference between the costs. So the title of the talk, what's the cost of an electric vehicle? It's really relative to the internal combustion engine vehicle. And we're relying on engineering and financial data that Yannik has collected. As you might expect, there have been many studies of electric vehicles, and this is just a small sample of the literature which is more oriented towards transportation economics. And what these studies do is some break-even analysis, right? So you vary your parameters and you see under what conditions, if any, the electric vehicle will be as cheap during the period of analysis as an internal combustion engine vehicle. I'll give you an example of that and say that the relative costs depend on how far you drive, how many years you own or lease the vehicle, and then of course the social cost of carbon. Now, there are websites which can be used for research as well as for the individual deciding whether to buy an electric vehicle, and if so, what case. And this is just a sample here, international and a couple in the United States. So what we do, following the typical practice in France, is to consider a lease of N years, and then it'll be 3 years in our analysis. It includes taxes because the taxes are a private cost. We look at the acquisition costs. So the vehicle is purchased, if you like, from the leasing company, and it's resold at a discount after N years. And the individual also pays the registration fee, the penalty for CO2 emissions and other taxes. And then in the case of electric vehicle, you have to buy the charger as well if you're going to do that at home. Then there's the operating costs, which include the energy, the maintenance, the insurance, and then a charger subscription fee if you want it, and that'll reduce the cost of recharging. So the equations here are pretty straightforward. The first equation says that the cost annually to operate the vehicle is the product of the price of the fuel, and then a factor which accounts for inflation, which could be specific to the fuel, whether it's petrol or diesel, and then the consumption per kilometer multiplied by the number of kilometers. Similarly for these other costs, and then a simple equation for that cumulative inflation factor. As far as the acquisition cost, we assume that the vehicle is not damaged when it's resold, and that the insurance that the person pays is for someone who hasn't been deemed responsible for an accident. Here are the equations, taking into account the technological depreciation, which depends on the type of the vehicle V, and then how many years the lease operates. Physical depreciation, which depends on those two variables plus the kilometers. And we assume that the two factors are interactive. So there's the resale value that the person will get at the end of the lease, equation for the cumulative inflation. And then if you do the same thing for the taxes and the electric charger, you get this as the equation for the total net acquisition cost. And then it's assumed that the person doesn't pay cash for the vehicle. Rather, they take out a bank loan at an interest rate of RB, and then they pay it back in equal annual installments over the N years. You get this equation for how much they're paying. Now, this is a comparison of costs, not the benefit that the person obtains from the vehicle. And there can be differences between electric and internal combustion. Charging time is a disadvantage for the electric, but there may be advantages in the quality of the ride. It's quieter, smoother. You're not changing gears. The privileges such as access to toll lanes without paying, and then feeding the grid. You recharge during a time of day when the price is low, and then you feed back into the grid at a time when the price is high. You can actually make money, and that also helps in terms of having adequate capacity in the electric system to meet the demand for electric vehicles as well as for all of the other uses. Now, the social cost depend on a number of things, and so far we've only included the greenhouse gas emissions. Local pollution matters a lot more, but that depends on where the vehicle is run, right? So you have to compare, let's say, center of Paris with rural areas, and then there's costs which are not known precisely for particular models. The extra cost of manufacturing the battery using raw metals, recycling the battery, and that technology is rapidly changing. And then there are other externalities where are common to both types of vehicles. Congestion is going to be the same if the vehicle's the same size. Safety, a bit of difference because the electric vehicles are heavier, which is good for the occupants, but bad for other people if there's a vehicle crash. And then the noise, the electric vehicle will have some advantage there. And what about the greenhouse gas emissions? Well, the cost of that for the electric vehicle depends on what source of energy is used on the margin. And this diagram shows you that cost varies greatly around the world. In the case of France, it's pretty low, 72 grams per kilowatt hour. It's cheaper in a few other places, marked in dark green, Scandinavia, for example, but it's much higher elsewhere. And the worst offender is Poland in the EU, right? The pollution costs are more than 10 times as big. Now, how do we deal with that? Well, there's a complication in the EU because of the emissions trading system. And in principle, the cost of the greenhouse gas emissions should be included in the price of electricity, but there's some debate as to whether that's the case. I think Stef has an opinion on that, and he can contradict me when he speaks. Right, so we're ignoring that. That's something to be looked into later, and it could take some time. And what about the emissions of internal combustion engine vehicles? So that's not yet in the ITEA system, although there's a plan to add it a couple of years from now. So what we do is we evaluate the emissions from the diesel fuel or the petrol fuel at 100 euros per ton. Some analysts think it should be perhaps double that, but this is a benchmark figure. And then again, adjustments should be made because the fuel taxes are pretty high, and particularly in France. And those taxes may cover externalities, although it's indirect. Right? So if you look at the taxes measured in tons of carbon dioxide equivalent, it exceeds the $100. Right? But those taxes are covering other things in principle, like congestion and so on, and also it's a revenue generator. So that's a complicating factor. And it's going to depend on the country. We have some information for France, but we haven't put it into the calculations yet. So the vehicle sample is this. There are 52 models, and they're either Mercedes or Renault. Of those 52, just over half are gasoline, 15 diesel, 6 plug-in hybrids, and 4 battery electrics, and none in the other two categories. 5 body types listed here from the smallest to biggest. And then, of course, the cost of buying the vehicle, leasing it, and then operating it's going to depend on the equipment. And we assume, or Yannik assumes, that it was the average equipment representative of the particular vehicle. So it takes a lot of information to get that for even a sample of 52. Now, the fuel consumption as well as the emissions will depend on speed and acceleration. And the way that that's measured is using the so-called worldwide harmonized light vehicle test procedure, which has replaced an earlier, less accurate system used in Europe. So what is done is the vehicle is run for 30 minutes over a course of 23 kilometers at different speeds, 4 categories. And the first is low speed. You can see a lot of start-stop, which is going to increase the emissions and the consumption of the ICEV more than the electric vehicle. And then 3 other increasingly speedy profiles, which are representative of rural travel. So what is done in the calculations is to consider either urban travel, which is going to be in the first category of the WLTP, and then the rural, which covers the other 3, and then take an average, so-called combined, for the representative traveler who does a certain amount of driving in the city and the rest outside. But in the case of the plug-in hybrid electric vehicles, you have to take into account what fraction of the running is done on the battery and what fraction is done on the fuel. In the urban area, it's going to be almost all electric, but the ICEV, or the internal combustion engine, needs to be run occasionally. Otherwise, it's going to stop working. You need the fluids to be circulated and so on. In the case of the combined, we have a formula, and I won't take the time to explain that. But it does mean that if you're going longer distances, then because of limited range of the battery, more of the driving will be done on the internal combustion engine. Here are the parameter values. I'll just highlight some of them. There's the pollution penalty, and it's actually a subsidy for the best vehicles, and that'll be in our example. And then the penalty can go up to 35,000 euros for an SUV with a engine over 300 kilowatts. So it's a great range there. We assume that the vehicles, regardless of type, are driven 15,000 kilometers. Well, that's not accurate, but in order to have a fair comparison between the two vehicles, that's the assumption. This is an average driving distance in France. The electricity cost depends on whether you're doing it at home, whether you have a subscription for which you pay annually, or whether it's without a subscription. You can see quite a difference in the prices. What about the inflation rates for the various components? Well, if you look at recent developments, there's been substantial inflation, the most for the battery electric vehicle, 11%, but that's not likely to persist. We hope that COVID doesn't come again and supply chain problems don't emerge. So what we do is we assume everything is zero, including the general inflation, which means that 5 minutes, the real prices, I have to skip some slides. To assume the real prices don't change. Right, so the comparison method, as I said, will involve trying to find two models, an EV and an ICE EV, which are comparable. So let's look at a case where they are very comparable because the body's identical. And this is one of the compact vehicles, a Twingo, the petrol version, and the battery electric vehicle. You can see that the battery electric vehicle is nearly 200 kilograms heavier, even though it's a battery of modest capacity. It has much less power than the internal combustion engine, and yet it accelerates a lot quicker, which shows you an advantage of electric vehicle, which is of course relevant to the customer, but since we're looking at costs, it's not a factor. The price difference before the subsidy is nearly 10,000 euros. It's substantial, but there's a $5,000 subsidy from the government, which reduces the cost difference to a little less than 5,000 euros. And then here the cost in the case of the combined driving, combination between urban and rural. The electric vehicle cost about 700 euros more, but the variable cost is about 250 euros per year lower. So the differential is around 400 or 500 euros. So let's look at how that varies now. This is the sensitivity analysis, so the break-even analysis, which has been done in other studies. So here we're varying the distance. We're assuming a base case it's 15,000 kilometers, and you can see that the battery electric vehicle is more expensive. That's 450 euros. But if you go further, then the electric vehicle gains an advantage because it's cheaper to operate, and then the break-even is about 27,000 kilometers. Few people actually drive that far, but you see, and someone who drives a great deal might find the battery electric vehicle cheaper. We vary the price of gasoline. Of course, it has no effect on the battery electric vehicle. The green line is horizontal, but the petrol cost goes up, and break-even is at about 2.30 euros, and the current price in France is about 1.83. So if the cost goes up by 50 euros per liter, then the battery electric vehicle will be cheaper. Then we can also vary how long the lease is. Benchmark is 3 years. If you extend it up to 10 years, which is as far as our calculations have been done, there's still a gap, but it's a lot smaller. Right? So longer lease is an advantage because the higher acquisition cost of electric vehicle matter somewhat less. So what I'll do, I'll have to skip this. So these are tables comparing the whole sample of 52 in terms of the body type, in terms of the power plant and increasing power, diesel, petrol, plug-in hybrid electric vehicle and electric. And the results are broadly consistent with what you get with the Twingo. Right, so I'll skip that and go to the greenhouse gas emissions. You get a difference between urban and combined. In the case of urban, a plug-in hybrid engine vehicle, which is comparable to the petrol, the engine power is the same. You can see the emissions are much smaller for the plug-in hybrid, but for the combined, the difference is much smaller because the plug-in has to be operated with an internal combustion engine, and then it loses the advantage of the lower emissions from the battery power. And then here's a case of roughly comparable models where the the electric vehicle has an even bigger advantage, both in urban and combined. So you can see the advantage there is with vehicle type and other things. Now let's look at the greenhouse gas emissions, looking well into the future. The left panel here shows the number of vehicles in the fleet in France. It's now over 35 million. And then at some future date, they're going to be all replaced by battery electric vehicles. And what we want to do is to see how quickly greenhouse gas emissions are going to drop. Well, that depends on the lifetime of the vehicle, since it's a survival function. How many vehicles ICE will still be operating so many years after they were operated. And then there's a new vehicle sales. Currently, it's a little under 10% in France. Target rapid increase to 40% in 2025. And then if the 2035 ceiling is binding, then only electric vehicles can be sold. Right. So this graph here is that's reproducing that. And there's the stock of vehicles, which of course 1 minute. Right. So that, and then here's the forecast of the CO2 emissions. Right, this is just repeating what was on the previous slide. And then you can see there's a decline in the CO2 emissions measured in grams per kilometer, dropping almost to zero in 2055. So let me skip about retrofitting. And here's the conclusion, really, and it's really looking ahead. What matters as far as the advantages or disadvantages of electric vehicles? Well, of course, a lot of things, and I'll highlight just three shown with the red arrow. Smaller batteries for urban driving. That was proposed by McKinsey in a report. So if you're going to drive your electric vehicle only in the city, maybe you have an internal combustion engine vehicle and you'd use that for rural, then why not install a much smaller battery? It'll be cheaper, the vehicle will be lighter, and the operating cost will be less. Another factor is that manufacturing electric vehicles is expected to be much less profitable than internal combustion engine vehicles. And the manufacturers, of course, want to make money. So what they may end up doing is charging people extra. And BMW is already charging people for heating the seats in the winter. Right, which means you don't really own your vehicle, that the company still has a control over you. And then the fiscal implications, and Stephanie Peer has a joint paper which addresses that very nicely. Right, if the electric vehicles are no longer paying fuel taxes, and maybe the operating costs are lower, so there's less general revenue obtained from them, then the government's going to be getting a lot less revenue. Some charges will probably be introduced, like distance-based, and that's going to reduce the advantage of electric vehicles. So I'm out of time. Thank you very much.
Two questions, one very helpful and one just broader. What's your question in terms of the given hybrids? I was corrected that you assume that 95% of units driven by given hybrids are electric.
In the city. But yeah, but not rural. Rural, it's going to be somewhat less than 50%. And Yannik, I don't know if you can, he's the expert, so Yannik can answer all the questions if he likes. Yes, yeah.
So you can give us a number, which is the resource cost of the car plus the environmental damage.
Yeah, well, that's something to be done, and it could make quite a difference, right? Because the battery manufacturing, as far as I understand, has as much environmental cost as the body. So that's going to be a disadvantage for the electric vehicle. And then what happens to the batteries? Well, sometimes they can be refurbished, and then other times you take the rare metals out of them, and that's most of the value. But of course, the profitability depends on whether lithium, cobalt, and nickel, and so on, what happens to the price. And they've been fluctuating. They reached the peak and they're coming down. You have new mines for lithium being developed. It's very rapidly changing environment. Yeah, well, the question had to do with the environmental cost of manufacturing vehicles, and in particular the battery for the electric vehicle. And then what about the disposal of the battery? There's going to be environmental cost, and then, of course,
Yes.
monetary cost as well. So how important are they, and how are they going to change in the future?
I think that the change in the future is today when we manufacture a battery, we import all the materials from other parts of the world. And we begin to see that by some manufacturers, for instance, Volkswagen, they have start a collaboration to recycle batteries. So what is very interesting to follow is the percentage and to control the percentage of the battery that will be recycled. Because when we recycle it, of course, we don't import any materials. And so the study begins to appear. What is important for us now is to have a good following of the percentage of batteries that will be recycled. It's very important for the social cost. And because it is a new technology today, the number is very small, but we can imagine, as you have seen the green curve presented by Robin before, that the percentage of EVs will increase very, very much. And so we have to control that the percentage of recycling battery increase exactly as the green curve. Very, very important for the social cost.
Time for one more question. Yeah.
You mentioned feeding back of electricity into the grid.
Yeah.
Is it already in place?
I think Stef knows something about that. If you want to answer that question, Stef.
I think it's not yet in place in many, but there are a lot of experiments, and it's really necessary in Western Europe, where we depend very strongly on highly fluctuating renewable electricity, wind, solar. And I think our computation was that it can make a difference of 300 to 500 euro per year extra benefit for the electric car. So, but of course, yeah, before people trust it, etc., you need an extra installation, you need a two-way interaction. And of course, I guess in France, they will be among the first to do it.
Yannik, do you think so?
Yes, partly. Yes, partly. The problem, of course, to manufacture battery in Europe, it's a good thing, and it is beginning. So we have seen in France recently the opening of several battery gigafactory in north of France. After that, the energy to use, it's a very, very difficult question. What is sure that in the 10 next years, we shall have clean electricity and much less clean electricity. And the nuclear plant will appear, the new nuclear plant will appear only in 10 or 15 years. And from today to this time, of course, we will have not sufficient clean electricity for everybody. So what we have to, there will be a choice to do. The clean electricity is for batteries, it is for heating people, it is for industry, it is for whom. So the increase of clean electricity is sure, but during 10 or 15 years, it will be not at all fully clean, not at all. And that is the question. And we have to take care to take the average electricity that we have in all our calculation, because we shall never know if it is clean or not clean. Exactly. And if we use clean electricity for heating people, it will not be used for battery. If we use it for battery, it will not be used for heating people and for industry.
The point I wanted to make is that sometimes we have really a lot of renewable electricity, like certainly in California during the day. So at that moment, you should recharge, and then this will be available for the grid in the evening hours. And in Belgium, we count on half of the maximum load for the moment. We count on electric vehicles to supply it at some moments. So we really count on it. And either it works, or otherwise we have to really install much more, say, peaking plants, things like that. But there's no other choice.
It's okay, thank you. This is joint work with two of my former students, Saskia Van der Loo and Inge Mayeres.
Okay. It's actually maybe somebody from DLR is in the room. It's actually part. Okay. Hi. We are part of a consortium looking at assessing what is the best way to decarbonize aviation in different ways. So this will be one of the models we could use for that. It's a little bit strange, but okay. Let me start by saying what is CORSIA. Maybe those of you who are not in aviation, CORSIA is an agreement reached within the International Civil Aviation Authority, some kind of United Nations body. And what is important, it caps emissions for international flights between two countries that signed the agreement. That's what we will try to explain. And then you are allowed to cap these emissions by the use of offsets. What are offsets? It's additional abatement in other sectors or by using sustainable aviation. Now, many countries signed, but what does it mean? Does it mean that we will see an effect? Yes or no? Okay. Is it important? Yes. Let's say if you look at percentage of the world emissions in aviation within the EU, here within the rest of the world, for us, everything is the rest of the world here, okay? Except for everything which is EU to rest of the world and rest of the world country to rest of the world country. So these yellow parts, they are covered by CORSIA. So it's a very important part of total emissions. Now, the second point to remember is that this is in principle covered by the Paris Agreement. Also, the US and China, they're also covered by the Paris Agreement. Everything which is inside the country is covered by the Paris Agreement, but this is covered by the CORSIA Agreement. Now, what I would like to discuss together with you is actually three problems that okay, so thank you. So what CORSIA hopes to, okay, this is the ambition of CORSIA, is that, of course, overall emissions of aviation went down in the last 2-3 years. But now they say, okay, we will try to stabilize at a given level, 2019, using, or this level, using different types of approaches, aircraft technology, operational improvements, SAF, whatever, so other types of fuels. That's the ambition. Now, I would like to discuss three issues together with you. One, and it's very often forgotten, is that international agreements are inherently weak. They are weak. And that's, I think, a very important point. So it will be, you have to study effective participation. Effective is not signing, it's really doing something. And it's very different. The second point is whenever you start to deal with offsets, you need credible offsets. A third point is very important. Carbon neutral is not climate neutral. Whenever you deal with aviation, it can be something very, very different. So what I will try to do is set up a very small model of participation decisions. I try to illustrate it numerically, okay, not for 190 countries, but for 10 countries, which we think are important, and try to discuss improvements through CORSIA. The first point, and let me repeat, this is an important point. An international agreement cannot be enforced. Nobody can tell you, you signed the agreement, you have to do it. No, because there is no sanction. There's no sanction mechanism. Imagine that the US doesn't comply with Paris. Can Belgium send a fighter jet to the US? So there is, and we say we gotta try to punish them with trade sanctions. Whenever a country starts to use trade sanctions, it also hurts itself. Okay, so it's very difficult to enforce. Even explicitly in CORSIA agreement, no country can punish a country that withdraws from the agreement. So it's very explicit. So the result will be very often close to Nash in the sense that you try to take into account where it benefits you, where it tries to avoid your type of damage. You will not take into account this world social marginal cost of climate, maybe 100 or 200 or 300. Okay, that will not be driving the behavior of the countries. Now, I know national politicians negotiate agreements. There's a way to explain why politicians negotiate agreements, but anyway, if the sanctions are weak, what you will see is that sometimes countries will try to comply with a green politician, and then you get a brown politician say, yeah, no, let's calm down. Okay, so this is a very important point. I'm not going to explain that. The second difficulty with offsets is that it's a compensation of aviation emissions by additional reductions in other sectors. It has to be additional efforts. And it's additional efforts on top of the Paris Agreement. Now the problem of who is going to certify that, who is going to control that. And it's actually kind of asymmetric information problem. I know there exists an international market of certified offsets, but when you look at the prices, they range from €1 to something else, while in Europe, the prices of ETS, which is a kind of certified followed up, is 50 to 100. So it's clear that countries that will participate will require quality guarantees, and they will probably say, okay, whenever I can buy something for €10 or for €1, it's not taken seriously. Okay. Third important point, whenever you discuss aviation, international aviation, is that carbon neutral growth is not the same thing as climate neutral. The reason is very simple, is that whenever you have emissions high in the air, you produce extra climate emissions, you produce extra climate effects, and they are well documented in atmospheric science. It's too difficult for me, but they exist, and okay, there is a peer-reviewed literature on that, and I think my take of that is that this represents whenever if you take 1 ton of carbon emitted in a car or in a truck, and you compare it with 1 ton of carbon emitted high in the air, it counts for 3 times more. There's an immediate consequence is that you say, oh, I'm going to compensate it with offsets. It cannot be correct. It cannot be correct. Even high quality offsetting is thus insufficient to compensate the growth in climate effective aviation. Okay, very simple idea. Okay, we're going to build a very simple model. The model will be extremely simple, okay, based on 4 assumptions. First assumption, country, representative citizen in the country, scores a linear utility function that is separable in a different international destinations. So no substitution event country A to B and A to C are no substitutes. It's not correct for tourism, but it's maybe makes sense for many other, let's say, types of motives. The second assumption, many people will object, the marginal production cost of applied is constant, and there is perfect competition, of course. Many people will say, yeah, doesn't make sense, okay, just to start going. The third assumption is that the stock of aircraft is homogeneous, okay, and its fuel efficiency is fixed. And have a look at the papers presented here by Jan and Fagina and Tuxedo. Also at this conference, they explain you how important it is to select the right aircraft, the speed of the aircraft, all these things. Final assumption, the marginal climate damage per country of a ton of carbon emitted on land is constant. You have a small sector, so I think could still make sense. These assumptions guarantee that we can study the participation question in a separable way. We can study whether A and B participate and whether C will participate. C and D does not affect A and B. Makes things much simpler. Okay, this is my model. As usual, extremely simple. what I do is, first of all, I switch to the energy dimension rather than the flight dimension. The energy dimension, I have here the price of aviation fuel. Here's the price level of kerosene. I keep it fixed, okay? Here I measure the quantity of fuel for intercontinental flight two ways, going there and coming back. Will be important in what is coming because I'm discussing connections between different countries. Okay. So what I have is I'm also going to assume that country B also participates. Okay. And more or less that there's an agreement on the price of offsets. This will be the price of offsets. I'm discussing here energy. So it's the same dimension. Kerosene, it means that whenever I need an offset, I will increase the price of energy used for aviation. Okay. I have a demand for aviation, which here is translated into energy demand. Okay, demand in 2019. I have a growth in volume, okay, of aviation. I expect by 2035, 2040 to have much more flight, much more activity. It can be maybe a little bit more efficient, but this will be the corresponding demand for aviation fuel in 2030. So I have here some kind of growth. Okay, what does CORSIA really promise? It promises that here the total emission or the total use of carbon in 2035, whatever, it should be here, okay, that this is reduced back to this level. I kept carbon emissions to the level of 2019. And this promise, okay, I will achieve it by using here in this case offsets. Offsets here, offset first effect to see is that of course price of using energy gets higher. I will have less flights, more efficient flights, whatever. So here this will be the first movement. I will reduce energy used by this part, and I will compensate this growth in energy by using offsets. So I will buy these amount of offsets to make sure that I stabilize emissions. Okay. The next step is try to make a model. What is the benefit of participating in this agreement? And here, what we see is we take into account what I explained before. First of all, the fact that I reduce energy use in aviation. Here, I have less aviation, less flights, less energy use, has a very big benefit. The benefit is 3 times larger than just the cost here, than the price of offsets. Because I count everything which is reduction of energy, I count it 3 times more. Because of my climate effect is much larger than my carbon effect. Okay, but I still have my offsets, and offsets also take part, also compensate or have some net benefits. What is the difference? I have to take into account that there will be grandfather permits. Okay, there will be this part compensation, producer surplus, consumer surplus. In addition, this is flying there and coming back. So I only have to count. You can see it in different ways. Only have to count half of the loss of consumer surplus and producer surplus, because interconnection between two countries is like a trade deal where you separate, you just divide the benefits. You can also say that half of the people are from another country, the other half are from my country. So there are different ways to explain it, but you have to make sure that you only use half of the loss of consumer surplus and producer surplus. Okay, let's move to the numerical application. I take 5 minutes, perfect. 10 important countries. I use expected growth rate, international aviation, price of kerosene minus 0.43, whatever. And then I use a national willingness to pay to avoid climate damage. And of course, yeah, you will ask a politician, yes, we will always say it's very, very important. And you will cite 200 euro, but I try to use OECD data on what I call some kind of effective carbon pricing, and I call that revealed carbon pricing. That's the best source I could find about what is the willingness to pay, national willingness to pay for of different countries for aviation. And I find some data, willingness to pay to avoid carbon damage counted at the level of land, okay, surface. Is 28, 13 for the US, here 13, Japan, whatever, and much lower for that. Then I use the model. How do I use the model? I start by fixing one offset price, let's say 28 euro per ton. It's about the price willingness to pay for avoid damage by the EU, okay? And I take one country here. For each country, I count different types of bilateral movements, bilateral flights. Australia, you go to Canada, and I compute here. In this case, 0.97 is the net benefit of Australia joining CORSIA if Canada also joins, because you need a bilateral agreement, okay? And you will see that here China is also benefiting for Australia, given their willingness to pay to avoid climate. China would also be interested, but China has a much lower willingness to pay, national willingness to pay for climate damage. Here is China, and China will not join CORSIA. So I have to check for different countries whether there is a bilateral possibility of agreeing. And I will figure out that Australia, Canada, EU, Japan, US will sign the agreement according to this type of computation. Important to see is that it's not simply 28 euro that really counts. It counts also whether the expected growth rate will count. You also have to take into account that whatever you actually, what you're actually doing is for a bilateral agreement, it's an opportunity to address emissions in both directions, okay? And given that consumer surplus and producer surplus only counts for half, so that's a very important driver for participation, okay? So growth rate will be important. Low offset price that everybody will join, but that's not serious, okay? Next point is, I have a graph that is missing, okay? That is important. Let me briefly explain. With these data, you can also try to see where it makes sense for duopoly. Duopoly in this case is Boeing and Airbus, where it makes sense to make an extra investment subsidized by the US and the EU. And we try to compute what would be the extra benefit, also in terms of participation and also in terms of reduction of emissions. So we made a small experiment. Imagine that flights become 25% more efficient, but on net terms, they do not cost less. They keep the same price, so we have no rebound effect. And then you can show the benefit would be of the order of 1.6 billion. And this 1.6 billion for the EU plus the US, you can compare it with the R&D budget of Boeing, which is 2.5 billion, something like that. So things are that order of magnitude. And that brings me to my conclusions. Okay. Still work to be done. Introduce blending mandate for SAFs. We are busy with that. I do not count too much on SAF. Add effects on connecting flights. There may also be cooperation beyond CORSIA. You can show that even if you cannot make binding contracts, it may be in your interest to sit together and do something extra, even if nobody can afford the contract. So that's something we still are working on. Add a supply model for aircrafts, which is, I think, a very important point for many people in the room, and add a supply model for aircrafts. That's it. Thank you very much.
So it's one thing to say that a country, quote unquote, joins, but who forces the airlines to do what they're supposed to do, namely buy off it? Is it public shame?
It's the CORSIA. The CORSIA agreement means that whenever two countries sign the agreement, flights from them and arriving somewhere else to do the necessary cap on their emissions. And then you can start to organize a tradable cap, or you can say,
So the country has the power to force the airlines to do
Yeah.
what they need to
Yeah.
do.
otherwise, of course, it doesn't work. Otherwise, you're right. So I didn't explain this, but this is the point.
So,
It's all in the most honestly that you have in this matter. No sense of what I want to.
It's important, and it also shows you that there is a difference between trying to offset and improving efficiency. Improving efficiency is much better than using offsets, and that's a very important point in terms of policy. That is an effort to it's important, and it goes for those you regarding plans and those increase trend.
Yes, we do have massive yes.
I think it's a factor two instead of factor 10, but at least I DLR.
We got given more recently that it was here, but the MS and finding my it is also more.
You're right.
Choose the job to like.
I think in fact
So we have like what and avoid these serious clouds, and that this is the best a lot. Yes, so saying.
it's important, and then okay, yeah.
This is this line here makes the soldiers with train tracks, but say they're
Right. And he's moving every like yes, but then I think probably the only way to force authorities to start thinking about a better flight schedule is to start taxing it. Otherwise, there will be many good intentions, but not so much will happen. And I think we talk about this for several years. Nothing has, because it's anyway difficult. It's a complex mechanism. It's very difficult to monitor. I still out a better flight schedule. You're right. So there is the other alternatives. Otherwise, there will be many good intentions. Something will happen. You're right. We can talk about several years. Nothing has. In fact, because it's anyway difficult. It's a complex mechanism. It's very difficult to monitor. It's the countries that will force their airlines, they will force, let's say, whenever EU starts to fly as a flight to the US, the EU, and both sign the agreement, EU and the US have to make sure that their total emissions hit the cap. Better their airlines, they will force, let's say, whenever, otherwise there will be many good intentions. Yeah, but they, if you're serious and because of your own benefit, your own damage that you want to avoid, you want to sign it and enforce it, it's a national country that can enforce it. It's just like in Paris, let's say the Paris Agreement, we have ETS in Europe and it's enforced. So here the hope is that every country that has signed, really serious about it, really wants to participate, will enforce it. Yeah, okay, I know, it's difficult to, you can do it in different ways. Here the both sides agree that we're serious about it, and we really wants to get it right. There, okay, I know, it's like, it's difficult to, end of the day, okay. From 2035 or 2040 to 2019, yes, what you want to sign and enforce it. It's a national country that can enforce it. It's just like in Paris, the Paris Agreement, and they need to compensate. It's a cap. So, and of course, you can start with emission in 2019. They can be grandfather. You can not grandfather everything. It's like ETS. You sell part of it or distribute part of it to those airlines that start. But so it's really no. That's the idea. If you sign CORSIA, you have to do it. It's really, you have to return to total emissions of 2019.
So on the x-axis, there's their emissions and not the fuel consumption. Maybe I didn't.
No, it's fuel consumption, but there is a one-to-one relation between fuel consumption and I forgot to mention that because it's only kerosene, so there's no choice there. Thank you.
No more questions. One pound. So CORSIA only wires to offset your
To offset your growth, yeah. Exactly. So it's very biased. I'd say it's an agreement, and I think there are much better ways of agreeing. Like Paris is a better agreement. Paris is just pledge and review. Every country can say, I promise this, and I may review it. But here you say, this is it. You have, and of course, if you're India or China, you expect much higher growth to certain destinations, you're punished. And so that's one of the points I wanted to show. These are the things you should improve. You're right. So that's probably the reason why India and China will not or do not join for the moment. Thank you. Thank you.
Okay, now we're moving on to maritime transport. So this is a joint work with my colleague Kjetil Fagerholt at the Norwegian Technical University and also Stef. So, and this work is part of a larger research project where we try to look at the technical and economic feasibilities of zero-emission high-speed ferries in Norway. So currently there are about 100 connections in Norway with high-speed ferries. Most of them operate in rural regions, and so far we have focused mainly on these rural ferries. But what we wanted to do with this paper was to look into the zero-emission high-speed and the role of both passenger-only ferries, as these are, but also the role of zero-emission ferries in this context. So, and then it becomes very interesting to look, of course, at the urban transport market that it is characterized by many externalities. For one that we pay special attention to here, it's of course road congestion. So on the one hand, you have the ferry, and it can alleviate road congestion, as it says here. But the ferries themselves have the problem that, especially the high-speed ferries, they have a very high energy consumption. So it's sort of trading off, on the one hand, congestion on the roads versus this very highly energy intensive and also emitting rural region. So of course, in this context, it becomes very relevant to risk at it's what about shifting from diesel ferries and then to low and or zero emission services that we focus on here. So I will primarily focus, because this is a very short range connection that we will look at, only focus on battery-powered services, but of course for longer connections, hydrogen becomes a viable option in these cases. So if we look at different policies that have been suggested, of course there are the IMO that focus more, I think, on the energy efficiency requirements for new ships and also reporting of energy efficiency for ships. EU now have, of course, maritime transport is due to be included in the ETS from starting next year, 2024. And of course, there are several aims to halve or cut greenhouse gas emissions that go along with these objectives. Norway, however, have an even more stronger objective of halving their domestic maritime transport emissions by 2030. And in order to reach this target, one of the main instruments that are thought of is actually to require zero emission services for both conventional slow-going ferries and high-speed ferries already from 2025. So all new ferries or ferry connections should be zero emissions starting 2025. So in that sense, it means that whenever a tender is renewed, which typically takes 10 years, then after 2025, the next tender should be a zero emission tender. Okay. So what we, in this context, would like to do is to understand the optimal planning of a high-speed ferry service in Oslo, the Norwegian capital. And our study basically, so in general, the literature on passenger-only ferries and the optimal planning of these, it's a scarce literature. And of course, if you downsize the scope of the study also to include zero-emission passenger-only ferries, then there are hardly any studies. So what we actually do is to extend our own study from last year in TRD by adding here the external cost of road traffic, because we look at the substitution between the road traffic and the ferry. Adding also crowding on board the vessel. And also we will also like to look at not only optimizing the current existing route, but also what about changing the actual route for the vessel service in order, for example, to save energy, to have a shorter sea distance and therefore save energy. So these are the questions we'll be looking into. Okay, so I will eventually go on to develop a larger optimization model, but in order to start off, we will just do the typical Stef way to provide a very simple graphical example. So what I'm looking at here is the urban transport equilibrium. I have end users that would like to go from suburbia into the city center. And their choice is either to go by car, then we have the user cost, or by the ferry. And currently, there's a diesel ferry in operation. And then we have the urban transport equilibrium here, currently at N0, where, of course, the user cost intersects with the car, with the diesel ferry. And then the question is, what happens when we go electric? Well, some of our previous studies shows that actually if you just keep the route at least fixed, and you say, I want to switch from the diesel ferry to a battery-powered ferry, you typically run into all sorts of problems with range. So typically, either in order to just uphold the same route and frequency, you typically need to add more vessels, or you have to actually slow down to save energy in order to make the stretch as planned, or the service as planned, and therefore it causes some disutility to the passenger because of added travel time. So in general, what we expect to see is that there's an upward shift in the user cost of the electric ferry users, and therefore you get a shift in the transport equilibrium from N0 to N star with fewer fast ferry users. And because of this, you have, as the shaded area here shows, an increase in the external cost due to that users now shift from the ferry to the road, and therefore you have more congestion on the road. So these are the features we would like to trade off in our model. So in principle, trading off both operator costs, the user cost for the ferry users, and also the potential added road congestion, shifting either to or from the ferry service. So we do this using a mixed integer programming model, where the model decides what type of ferry to use in terms of passenger capacity and also speed choices, and even more battery sizes for different ferries. The fleet size, of course, and then the frequency. And because this is also a battery-powered ferry service we're talking about, we need to determine the number of chargers needed along the route, and also what the installed capacity of these chargers would be in terms of megawatts. The objective of our optimization model is to minimize costs, taking into account both the capital costs, the investment costs for both the infrastructure, the vessels, of course, the operator cost in terms of energy and labor, the waiting and transit time costs. We also here include the transit time cost of passengers in transit while charging, when you're sort of stuck on board the vessel while charging, and also then the external cost of diverted traffic to or from road transport. And we optimize this under set of constraints that we should have saturation of passenger demand on all links of the maritime transport network. Of course, we need to have sufficient installed capacity to manage the energy demanded by the ferries of all the charging points. And then we assume that all operations that are planned in terms of transit time, charging time, a passenger going on and off the ferry, everything has to take place within a given planning horizon, which in our case, we look at a commuter service that operates for 4 hours in the morning peak and 4 hours in the afternoon peak. So we will then use, everything needs to take place within 4 hours. So that's the main constraints in this problem. Okay, and of course this is a large model and quite a few parameters included in this model, so I cannot really cover all, but I will just talk briefly about some of them. So this is the case that we study. This is a vessel route B20 in Oslo that goes from Aker Brygge, which is in the heart of Oslo, out to Vollen and Slemmestad, and then back again to Aker Brygge. So the current service is operated by one vessel that makes 3 round trips within this 4-hour time span in the morning and then the same time. So that has a frequency of 3. And this ferry competes readily with the highway E18, which is one of the most congested highways in all of Norway. So we are sort of very interested in looking at this trade-off between the ferry on the one hand and then road congestion at the E18. Okay, so we start off with an OD matrix for travelers, and we will only focus on the afternoon peak because that's the dimensioning in terms of the number of passengers using this ferry service. And then we take this as the point of departure and calculate the user cost of the ferry. And then we look at what the user cost would be with other alternative service levels in terms of the size of the vessel, in terms of the speed of the vessel, etc. And then we compute the alternative demand for each of these scenarios. No, so in general the traffic here is very low. So these are just number of persons. Yeah, surprisingly low, I should say. Yeah. So what we do is then to start off with computing the demand for all kind of service level, and then we use that as an input to the optimization model. So we do this using an own price elasticity to compute the change in ferry demand, and then we use diversion ratios to compute how this change in demand is transferred either to car travel or to bus travel. And then we use estimates of the external costs per kilometer to calculate the external costs of the road transport of the passengers that either are converted or shifted from the ferry or to the ferry when the ferry service changed compared to the current situation. Okay, and then we also include a piecewise linear value of time function to a price crowding on board the vessel. So this is just adapted from the latest version of the Norwegian valuation study. And then we also have quite a few vessels or vessel types that this model can choose from. So the different vessel types, they vary according to the number of passenger or the passenger capacity, what kind of the size of the battery of the ferry. For battery-powered ferries, of course, we also have both diesel ferries and we have battery-powered ferries because we would like to compare the two. And then they also vary in terms of sailing speed. So we assume here that the model can select between ferries traversing at 15 knots, 20 knots, and then up to 25 knots, where 25 knots is the maximum speed limit in the Oslo basin, more or less. Yeah, and the one here in black, that's the current vessel that carries 250 passengers and operates at an average speed of 21 knots. So we will also use that for comparison. Okay, so I will just quickly go through the main results. I will start with the optimization of the current service and then go on to look more at what if we change the existing route or the existing service. How will that influence our results? So here I'm comparing, so this is the optimal solution for a conventional service and for a battery-powered service. And we see that in both cases, the MIP model selects one vessel that operates within this 4-hour period, that operates the round trip 3 times. So that's the same as the current frequency and the current number of vessels. However, the passenger capacity of the vessel is reduced slightly from 250 which was the current passenger capacity, to 200 here. What we found to be quite surprising compared to our previous results on these high-speed ferries is that the optimal selected speed is 25 knots, both for the battery-powered and the conventional case, because previously we have studied and compared conventional vessels and battery-powered vessels on a longer connection. And what we see then is typically that the diesel ferry would like to go at maximum speed to save passenger time, but for the battery power vessel, it becomes a trade-off because it has to slow down to actually manage this operation with, say, if you start off with comparing one vessel to one vessel, because if it doesn't slow down enough, then it has to operate with two vessels, and then it becomes very much added operator cost. But in our case, we have a very short connection, and in this case, range is not a significant problem. So the speed here becomes the same for both the battery-powered and the conventional service. And since the current speed is 21 knots and the optimal speed is 25 knots, we actually have a slight number of passengers actually going from road transport to the ferry. And in our model, that is sort of accounted as a negative cost or a subsidy for the ferry operator. So a slight increase then in the number of passengers. The model also here selects only one charging point. It's sufficient to have only one charging point at Aker Brygge with the installed capacity of 3 megawatts, which is kind of in the standard range, I think, for currently with slow-going ferries. About 20% of all ferry connections in Norway now are battery-powered. And I think between 2 and 5 megawatt is a typical installation for these services. So this is in the ballpark. And then, of course, if we are switching from optimized conventional to a optimized battery-powered, this would save us 2.7 ton of CO2 emission in this period. So, and that number becomes very handy later when we can actually compute abatement cost per ton of CO2 saved. Okay, so if we look at the costs and the cost decomposition, so in general, the gap between the cost of the diesel and battery powered is about 7,000 Norwegian kroner for this 4-hour period, which amounts to about 720 euro for this period, and could be translated into abatement costs of about 2,500 NOK, Norwegian krone, per ton of CO2, which is slightly higher than the benchmark for CO2 price that the Norwegian government has set to 2,000 krone per ton in 2030. So this is somewhat close to passing the cost-benefit test for this short-range service, but not yet fully there. So, but this is much better than a previous result for this more rural connection that shows abatement costs of up to 30,000 NOK per ton, so a substantially higher number. So if we compare the cost breakdown here, we see, of course, that the value of time of passenger is really what counts. But since this is equal, I think the main interesting thing here is to see that the energy costs are slightly less with the battery power because it's a more efficient propulsion system. However, the installation or the capital costs become higher because now you have to have all this added infrastructure that goes along with the battery-powered service. Okay, so we do some sensitivity of this initial test, for example, comparing with this the current vessel type. In this case, we see that the abatement costs become about zero, because in some sense you start off with a non-optimized service and compare to an optimized service. And then our point is really that if you can, when you replan your system while introducing battery-powered or zero-emission technology, you should make sure to mitigate all kind of inefficiencies that currently already exist in the system in order to sort of lower or reduce the abatement costs related to the transition from the conventional propulsion system to the zero-emission propulsion system. I think the main interesting finding we had with this sensitivity test is that In this case, we restrict the maximal installed capacity for the chargers to be only 2 megawatt. Remember that in the optimal solution, the model selected 3 megawatt. What if we restrict it at 2 megawatt? And also, what if we choose another set of energy prices, both for MGO, but also for electricity? We see here that the solution and the abatement cost calculations are very sensitive to access to grid capacity and energy prices. So I think this is, we see now that there's hardly any more. So in Norway, everything should become electric, and there's no more grid left. So expanding the grid is going to cost substantially also in the future. Okay, so what we then go on to do is to say, okay, what if we also could look at an alternative route? Because range is typically a problem for these vessels. So what if we can actually have a different route where the sea lag is shortened here? So we only operate the vessel between Aker Brygge in the city center to Vollen, and then we have a bus replacement service from Vollen to Slemmestad at the disutility of the people from Slemmestad, of course. We see that in both cases, both for the conventional, so I'm comparing here the base scenario where I just maintain the route as fixed as it is today, and then with this alternative route scenario, I see that the total costs of operating the service is reduced both for a conventional service and a battery-powered service. But also the interesting part here is that if you say that my benchmark really is the current service, but now I want to go electric, how can I save costs? Well, you then also have, of course, other options beyond just the technical replacement of the vessel service. You can also have an operational measure, which is then to change either your route or to change your frequency in order to save the cost of this transition. And of course, you see here that if you compare the conventional vessel in the base scenario with the current route to the cost of operating a battery-powered vessel with the alternative route, you can actually have in some sense, negative abatement cost also by making this shift of route alongside the shift in propulsion system for this vessel service. And I think the final thing we were interested in looking at was whether actually just closing the service altogether would make sense. So then we do look at the current cost of operation is about 150 KNOK for this period. The external cost from the diverted traffic from closing the service is here computed at 32.8 KNOK. Okay, so then it's in some sense a question whether this service should exist all together. But I think what we learned from this is that actually with this short range connection, because in the previous project we looked at much longer connection, and of course most of these high-speed connections in Norway are much longer than this service. Range really matters. So of course having these battery power services could be useful and also profitable in some cases, but I think range, then you really have to have a very short range connection. Because typically when the connection becomes longer, it's not even viable with batteries or even battery swaps. You need to go to, for example, hydrogen, and then the costs really explode on this system. And I think also a valid point is that if there are some inefficiencies already existing in the planning of the current transport system, they should also be mitigated when you make this transition in order to sort of reduce the abatement costs of going from diesel to a battery-powered or zero-emission service. But I think what we highlighted here is, of course, having enough grid capacity and low energy prices could also make a substantial impact on the cost of having these battery-powered or zero-emission services. Yeah, and I think also what we're trying to tell all stakeholder partners involved in our research project on this is that you should think outside the box, because what the politicians want is just to have the current routes and the current timetables, and nothing else should change than the vessels. But we try to tell them that maybe you need to, so if your cost structure change because of you got new vessels with completely different properties, maybe your planning of the operations should also change alongside this. So the typical example we have is that actually what we see is that by changing speed for some connection, you can actually, because range is typically a problem, and often the answer would be, okay, we cannot make this with batteries, this connection here, we need to go to hydrogen, say. But what if you change speed? Then you can actually manage this connection with batteries and save substantially from this. So I think actually having also thinking about the technical measures, it's of course important, but to join it, also think about the operational measures and how to replan the service when your cost structure change. I think that's a vital and important message for the decision makers. Of course, they don't listen, but that's a different story. Okay, thank you so much. Okay, any questions?
Yeah, I was thinking of some considerations and whether you've included them in your cost-benefit analysis. And one would be the cost of replacing ferry batteries.
Yeah.
The second would be the access time for the traveler. Right? And access time is probably minimal for driving a car, but it would be a getting to the origin and then the destination in each way. And then finally, you have the Norwegian toll ring, right? And would the people who drive pay a toll? Because that's a social cost, a private cost, but not a social cost. So those are three factors.
Yeah. So the first one, replacement, yes, that's included here in the computation. The second one was access costs. It's not fully included, I have to say. The third one was, what was the third one?
Yeah, the toll.
Yeah, that's also accounted for. So that's subtracted in the calculations here. Yeah, because we have this cordon tolling in Oslo. Yeah, that's true. Yes, there's a question.
As for presentation, for the users of the vessels, there should be an economical scale, right? So reducing cost, but in your plot, you were showing increasing cost. So I'm wondering why is that?
So I think you refer to this graph with the value of time. Yeah, so the idea here is that when the vessel becomes very crowded, so we had this kink at 40% capacity and also at 80% capacity. So when the vessel becomes very full, the disutility for the traveler becomes much higher. Was that your question, or?
No, actually it was the other plot, because for low demand, there is the utility of having more frequent service. But in the plot, which you say this is a style of plot, that there was always increasing the user cost of the vessel, and I don't understand why it's not decreasing. In the plot.
Okay, let me just find this plot. Oh, sorry. You mean this? No, okay. I'm not sure which.
Yes.
Oh.
It was my mistake. So why the user cost is decreasing?
Yeah. You have to answer these questions since you have made the illustration. But so of course this illustration is not. So we of course have an optimization model that is the sort of the main analysis that includes much more components and much more detail than this model. So what we wanted to do here was just to have this very brief, not true to the model results, I think, was not really tailored to the model results. Maybe we should think about doing that, but so that, sorry, go ahead,
It's a
Stef.
much more complicated public transport model, but the idea was just to show that whenever public transport is forced to be electric, it will become more expensive, and for that reason, we will increase other externalities on the road. That was the main idea, to put it in one figure, and not more than that. Sorry, and I think in the operational model, actually the model is taken much more seriously. It's done much more seriously. Okay, you have to explain very often to people that do not know this. Okay, and say you have to visualize, and that's all. Sorry.
Yes.
I have another question to this figure. What you did, my first question is you calculated changes in external effects in the competing modes of the ferry.
Yeah.
Did you also calculate changes, for example, in tax revenues in the secondary markets and changes in subsidies? Because that could also happen here because you have more car driving, so you can collect more taxes.
Yeah, no, this is done very stylized in the sense that we only look at the number of people going to and or from the ferry, and we only look at the change in external costs or net external costs subtracted of the port tolls only for these ferry users.
Do you have marginal social costs of the ferry?
Of the ferry?
Of the ferry, the emissions, for example.
Sorry,
The marginal social costs of the diesel ferry emissions?
I think that's taken into account the marginal external cost of the ferry, of the diesel ferry.
Yeah.
I think that's taken into account.
Yeah, so we of course make the simplification here that we only use clean energy for the battery powered propulsion. So we disregard the CO2 emissions from the.
Argument, higher costs for electric ferry and higher social costs for car, but you may have lower social costs as well.
Yeah, but that's something you, okay. You can add also external costs, but the main idea of this graph, and don't overestimate the vision of this graph, is just to say that if you make public transport more expensive because you want to be electric, the risk is that you will have more people, more congestion on the road, not more than that. And of course, all the other external costs are taken into account in the optimization. But sorry.
I think what we see is often very hard to tailor this, to make this very informative graphs and try to sort of motivate this optimization problem, because the optimization problem has so many details. It's very hard to cover them all in this figure. Then it becomes impossible, intractable in the end. So, okay, any other? I think we're out of time already.